Alright, in this video I want to introduce the concept of buffers. So buffers are solutions containing weak acids and their conjugate bases. And buffer solutions have this special ability to resist pH changes. And I want to go through a few examples at the beginning of this video to show you mathematically and chemically how they do this. So let's first look at an example where we don't have a buffer. So if we don't have a buffer, we would expect that we can't really resist pH changes very well, right? In the absence of a buffer, our pH is going to be disturbed quite easily by outside substances that we add into our solution. So let's take, for example, 1 liter of pure water with an initial pH of 7. So that doesn't have any weak acids or conjugate bases, so there's nothing in here that would give this the special property of buffers that would allow it to resist pH changes. So let's see what would happen when we add in 0.15 moles of potassium hydroxide. And we know that that is a strong base. So we would expect, if this solution has no ability to buffer or it has no ability to resist pH changes, that this strong base is going to raise the pH of 7 quite significantly. So when we drop 0.15 molars of KOH into this solution, it's going to break up into K plus and OH minus. And we know the K plus has no effect on the pH, so it's really the hydroxide ion, the OH minus, that we're going to have to account for. So we know that 0.15 moles of hydroxide are going to be floating around in 1 liter of total solution, and that is going to give us a 0.15 molar concentration of hydroxide. So in order to find the pH from this change, we're going to first have to find the pOH since we have hydroxide. So pOH is the negative log of OH minus, and when you plug in 0.15 here for your hydroxide concentration, you get pOH of 0.83, and then since we know pH plus pOH is 14, we know that the pH is 13.7. So notice here, our initial pH was 7, then it went to 13.17. That is a massive increase, especially for pH, because we know that for every 1 point increase in pH, we actually got 10 times more basic. So you really can kind of get a sense for the magnitude of how much this KOH is able to disturb the pH of this pure solution of water. Right, in this next example, example 2, we're going to look at another situation where we have no buffer, and we again perturb the pH by adding in 0.15 moles of potassium hydroxide, a strong base. So remember, buffers are solutions containing weak acids and their conjugate bases. And this time I'm saying the initial solution is 1 liter of 1.15 molar HF, or hydrofluoric acid. So that's a weak acid, but there's no conjugate base in there, right? The conjugate base would be F minus, or fluoride ion, and we start out with none of that. So now for an example, let's see what's going to happen when we add in this KOH. So in order to find what's going to happen to the pH, we need to find the initial pH and then the final pH. So this is actually a fairly involved process. As you can see on the board, there is a lot of work written here. And this was essentially what we learned how to do for exam 4. How to find the pH of a solution after you add in acids, bases, mix them together, and so forth. So to start out here, we'll find the initial pH. And to do that, we say, okay, the hydrofluoric acid is going to dissociate into H plus and F minus. So for that reaction, we will set up a rice table, because remember, that's all we started with, hydrofluoric acid. So we started out with 1.15 molar, that was given. And then we start out presumably with no H plus and F minus before it dissociates. So the change will say minus X plus X plus X. And then we get our equilibrium row by adding the initial and the change together, and then we're ready to set up our equilibrium constant. So for this we will need the Ka of HF, which you can get from a table, and we do products times products over reactants, and in this case you actually can utilize the shortcut rule, because 100 times 6.6 times 10 to the negative 4 is less than 1.15. So when you solve for X here, you'll get 0.02755, which you can see is going to be the concentration of your H plus ions, which allows you to solve for the pH. So we know that pH is the negative log of the concentration of our hydrogen ions. And when you type this into your calculator, you should get the initial pH is 1.56. So quite an acidic initial pH, as we would expect with a solution containing just an acid, even though it is a weak acid. Okay, so now let's disturb this pH by adding in some KOH. So remember, this is not a complete buffer. It's a weak acid, but it doesn't have a conjugate base. So we would expect perhaps a weak buffering effect, but not a complete buffering effect. So maybe this will be better at holding its pH than pure water was, but still not as good as a bona fide buffer. So let's see what's going to happen to the pH. So step one, we have in any neutralization reaction, remember we have an acid here and a base here, so this is going to be a neutralization reaction. Step one, we let the initial compounds dissociate into their ions. So KOH is a strong base, so it'll dissociate into K plus and OH minus. And then HF is a weak acid, so it is actually not going to appreciably dissociate for a neutralization reaction. So we consider HF to be reacting with these products. And we know that K plus does not have any effect on our pH, so we just say HF is going to neutralize OH minus, or vice versa. So step two, we set up that neutralization rice table by saying HF plus OH minus goes to its products, F minus and H2O, and we know that our initial amount of HF was 1.15 molar. We were given that information. OH minus, well, we found from 0.15 molar that if this is a 1 liter solution, and we know molarity is moles per liter, so 0.15 moles over 1 liter is 0.15 molar, and then we have no F minus to begin with, and then H2O we don't have to consider in equilibrium expressions. So we'll say that 0.15 is going to be our limiting reactant because we have the least of it, and these all react in a 1 to 1 to 1 molar ratio. So we'll lose all of the 0.15 from our reactants, and then we'll gain 0.15 in our products. So then we'll be left with 1 molar of HF, 0 molar of OH minus, that was our limiting reagent, of which we used all, and then F minus we had 0.15 molar at the end. Okay, step three in any neutralization reaction is we reverse this reaction here and then draw our last rice table. So this is just what you do with neutralization reactions. It doesn't make the most intuitive sense, but this is just what you have to memorize. So F minus plus H2O goes to our what used to be our reactants. Now they're our products, and we know we ended up with 0.15 molar F minus, no hydroxide, and then 1 molar of our HF, and then our change is going to be minus X plus X plus X, and then equilibrium we simply add together the initial and change rows. And then in this case, we actually have to use HF's KB because Ka describes HF going to H plus and F minus, right? That's why we used the Ka for this rice table. But here we're going from HF, F minus to HF, so it's reversed. So in this case, we actually have to use the KB for HF. So we know that Kw equals Ka times Kb, and we can solve for the Kb because we know Kw is always 1 times 10 to the negative 14. Ka is 6.6 times 10 to the negative 4 like it was here. And we simply solve for Kb. So that's what we'll use for our equilibrium constant. And then 1.52 times 10 to the negative 11 times 100 is less than 0.15. So we can use our shortcut rule and ignore this minus x and this plus x. So we get x over 0.15. If you solve for x, that will be your hydroxide concentration, 2.28 times 10 to the negative 12. And then the POH is the negative log of that hydroxide concentration, which was 11.64. And then finally, we know that pH is 14 minus the POH, which ends up 2.36 after we add in this potassium hydroxide. So you can see here, although the potassium hydroxide did raise the pH from 1.56 to 2.36, it wasn't quite as much as the pH was raised when it was pure water. Remember, when it was pure water and we added in the same amount of potassium hydroxide, the pH went from 7 to over 13, so that was a massive increase. This is relatively smaller, in terms of pH change. And in the next example, we'll see that when you have a true buffer, the pH change is even less. It's minuscule. So let's look at that next. Finally, moving on to the example where we have a true buffer. And just to remind you, a buffer is a weak acid and its conjugate base. So here we have hydrofluoric acid, a weak acid, and its conjugate base, the fluoride ion. And again, I want to see what's going to happen when we try to perturb the pH of this system to test this buffer's ability to resist pH changes. So the first step here is we have to find what the pH started at. And to do that, we know that we can set up a rice table for the dissociation of hydrofluoric acid into its ions. And we know that the initial amounts and concentrations were 1 molar hydrofluoric acid, we were given that. We had no initial hydrogen concentration, and then an initial 1 molar fluoride concentration. And then we'll set up our change row, minus x, and plus x, and then add together the initial and the change to get our last row. And we already know from the last example that the Ka of hydrofluoric acid is 6.6 times 10 to the negative 4. And in this case, that is, if we multiply that by 100, that is less than 1, so we can use our shortcut rule. So I'll ignore this plus x and this minus x. So this will leave me with x over 1 for my products over reactants. And then when I solve for x, look what I'll get, the hydrogen concentration. So when I take the negative log of that, I'll get pH equals 3.18. So that's our initial pH. Now to find the final pH after we add in potassium hydroxide, our strong base. And again, this is a neutralization reaction, and this is a fairly involved process, but I think it's good practice for you guys. So step one, you always see what's going to happen to your initial compounds. So potassium hydroxide is a strong base, and therefore it will dissociate completely into its ions, potassium and hydroxide. And then hydrofluoric acid is a weak acid, so it will not dissociate appreciably into H plus and F minus for the purposes of a neutralization reaction. So we will be left with HF, K plus, and OH in the solution, but we know K plus has no effect on the pH, so we will simply let HF neutralize the OH minus in a rice table. So that's step two. We set up our rice table, and we know our initial amount of HF was 1 molar. Our initial amount of OH minus, well, we know this came from KOH, which is 0.15 moles, and we're assuming this was a 1 liter solution. So that will be 0.15 moles per 1 liter, so 0.15 molar. And then fluoride ion, we know that that started with 1 molar concentration. That was our conjugate base. So notice how this is different from the last example. Now we have a conjugate base to go with our weak acid. So we would expect this pH change, pH to be resistant to change. So this will be our limiting reagent here, the OH minus. So we'll lose 0.15 from both of our reactants in concentration and gain 0.15 in our products in concentration. So we'll be left with 0.85 molar hydrofluoric acid, no hydroxide ion here, and then 1.15 molar fluoride ion. And then on to step three. For any neutralization reaction, step three is to reverse the reaction in step two. So we'll let fluoride react with water to make hydrofluoric acid and hydroxide ion. So we know the initial amount for this reaction of fluoride is going to be from here, 1.15 molar, and then the initial amount for hydrofluoric acid, we'll get that from here, 0.85 molar. We don't worry about water in equilibrium because it's a pure liquid and it doesn't affect it. And then hydroxide, we started with none of that for our step three. So we'll do our change minus x, and plus x. So we'll get our equilibrium row by simply adding together the initial plus the change. And then you should get to a point where you have to use a KB here, because remember, HF, when it goes from H plus to F, we use our Ka, but Kb is used in cases where you're going the reverse direction. So we're going F minus 2HF, right? So now we have to find the Kb. We actually had to do this last problem. So this is going to be Kw equals Ka times Kb, and we know the Ka, 6.6 times 10 to the negative 4. Kw never changes, it's 1 times 10 to the negative 14. So we simply solve for Kb here. We get 1.52 times 10 to the negative 11, and then we'll set that equal to our products times our products over reactants. And in this case, 1.52 times 10 to the negative 11 is a very small number, and thus the shortcut rule applies. If we multiply this times 100, it's still less than 1.15, our initial reactant concentration. So solving for x here will give us, look, our concentration of hydroxide ion. So when we do POH, we'll do the negative log of the hydroxide ion concentration, and we'll get our POH of 10.67, and then we know our pH is equal to 14 minus 10.67, which will give us a final pH of 3.31. So see how this pH, 3.18, is quite similar to the final pH, 3.31. Those are pretty close together. So this shows you mathematically how a buffer works. It resists changes in pH. So even though we're adding in a pretty good amount of strong base here, our pH does not rise significantly. So buffers are very important because, for example, the pH of your blood has to remain constant. So buffers in your body are vital to keeping your pH stable. So I'd like to quickly recap what happened here. So in our first example, we started off with pure water with a pH of 7. We then added 0.15 moles of potassium hydroxide, a strong base, to raise the pH. And the pH was quite responsive to that addition of the base. The solution of the pH went up a total of 6.17 points, so 7 to 13.7. So on a pH scale, that is a massive change. Example 2, we started off with a solution of solely a weak acid, 1.15 molar of hydrofluoric acid with an initial pH of 1.56. We then added a 0.15 mole amount of potassium hydroxide, and the pH went up, but not nearly as much as it went up in the first example. This time it only went up about 0.8. So still, a noble increase on the pH scale, but not nearly to the scale of the sensitivity of pure water to the addition of a strong base. And then finally, example 3, we had a true buffer. So we started off with 1 molar concentration of hydrofluoric acid, a weak acid, and its conjugate base, the fluoride ion. And we had equal amounts of both, and this generated an initial pH of 3.18 in our solution. And upon the addition of 0.15 moles of potassium hydroxide, the pH raised very slightly to 3.31, only by 0.13 points. So you can see here the mathematical effect of having in place the definition of a buffer, a weak acid and its conjugate base. So again, I'm showing you these to highlight the effect of a buffer and its ability to very tightly regulate the pH of a solution. Okay, now I'd like to go into chemically, how does a buffer actually do what it does? We know a buffer resists changes in pH, but how does it actually do this on a chemical level? Well, we know a buffer contains a weak acid and its conjugate base, so I wanted to use the same example we did where we had hydrofluoric acid, a weak acid with its conjugate base, the fluoride ion, and how they sort of quote-unquote take the hit for the solution by getting rid of the two things that we know to affect pH the most. So we know that hydroxide ion and hydrogen ion have a severe impact on the pH of a solution. So what the weak acid actually does is it quote-unquote absorbs the hydroxide ion by reacting with it to make the conjugate base and water. On the other hand, the conjugate base quote-unquote absorbs the hydrogen ion by reacting with it to make weak acid. So you can see that in both cases here, the conjugate acid and the conjugate base sort of get rid of or soak up the hydroxide ion and the H+ ion out of the solution, thus resisting any significant changes in pH. Okay, the next thing I'd like to mention is the Henderson-Hasselbach equation. So this equation is very important for buffer systems. So this says that the pH of a solution is equal to the pKa of the weak acid that you're working with plus the log base 10 of the concentration of the weak acid's conjugate base. So this, for this example, would be F minus, or the fluoride ion, over the concentration of the weak acid, or hydrofluoric acid in this case. So if we wanted to apply this buffer system to the Henderson-Hasselbach equation, we would have to find the pKa of hydrofluoric acid, which we could find fairly easily off of a table. And then we would need to find the concentration of the fluoride ion in our solution and the concentration of our hydrofluoric acid in solution, and that would be F minus over HF. And something special happens when A minus equals HA in terms of concentration. So again, this would be like our fluoride ion, so we could plug in F minus for here, and then hydrofluoric acid, we could plug that in for our general HA acid. If these two equal each other, think about what's going to happen to this fraction here. Well, it's going to be 1, right? And we know that the log of 1 is 0. So then if these two are the same, this whole term goes to 0, and pH equals the pKa. I'd like to conclude this video by mentioning a few strategies that you can use to design the ideal buffer. So number one, you want to pick a weak acid with a pKa close to the desired pH of the solution. So for example, let's say you want the pH of your solution to be 7.2. Well, you'd want to pick a weak acid with a pKa as close to 7.2 as possible. This will help the buffer do its job. Okay, the second strategy is make your concentrations of weak acid and its conjugate base big. Make them large, because the more of the conjugate base and the weak acid that you have, the more they'll be able to resist perturbations to the pH. So for example, you remember we added in potassium hydroxide into our solutions with those 3 examples. If we had added in a huge amount of potassium hydroxide, even though we had a buffer in that 3rd example, we could overwhelm the buffer. So, you're only as good as the amount of buffer you have. So you want a lot of weak acid and conjugate base. And then thirdly, you want to make the ratio of the conjugate base to the weak acid equal to 1. This will make it so the solution is ideally buffered in both directions. In our examples, we used a strong base to add into a solution, but we could have just as easily used an example where a strong acid was added into a solution. So remember, the weak acid sort of soaks up the hydroxide, whereas the conjugate base sort of soaks up the hydrogen ion. So if we have equal molar amounts of these two things, we're ideally poised to resist changes in both directions, both acidity and basicity. So you want this ratio to be 1. So I really hope this video helped you guys out. If you'd like me to make more, please contact me on my Facebook page, facebook.com/denovotutoring, and good luck with your studying, guys.